right now, at this exact second, millions of invisible computers are frantically screaming at each other right behind your screen.
Yeah, literally millions of them.
And the only thing keeping the entire internet and, our modern digital lives from just collapsing into total anarchy is a set of mathematical rules invented by a guy who, well, he basically just wanted an easier way to format his book.
It's such a wild origin story, honestly.
Welcome to this deep dive. Today, we are pulling from a comprehensive stack of sources, primarily a really detailed Wikipedia article, to explore the life and mind of a true pioneer, Leslie Lamport.
It is a phenomenal story. I mean, we are talking about the architect who figured out how to bring order to the invisible chaos of computing.
And what a time to look back at his work, considering he just retired in January of 2025.
Right, just recently.
Yeah. He wrapped up this completely legendary career spanning Massachusetts Computer Associates, SRI International, Digital Equipment Corporation, Compaq, and of course, Microsoft Research.
That is quite the resume.
It really is. We are going to explore how he, tamed the internet, built the exact tool academics used to write their papers, and then tried to save software engineers from themselves. Okay, let's unpack this. To understand what Lamport actually solved, we first have to understand the nightmare he walked into. What exactly is the arena he was working in?
So Lamport's main arena is a field called distributed systems.
Okay.
And to visualize this, you kind of have to abandon the idea of a single, giant, all-knowing computer brain.
Like a mainframe or something.
Exactly. A distributed system is a network where several autonomous computers have to communicate with each other to get a job done.
Right.
And they do this by passing messages back and forth.
So there isn't like a central boss directing traffic?
Nothing of the sort.
Yeah.
They don't share a single physical clock, and they don't share a single memory bank.
Wow, okay.
Yeah. They're entirely independent machines spread out across different locations, but they somehow have to act as one cohesive unit.
That sounds like a mess.
It's a massive headache. If one computer fails, or a message gets delayed on a network cable, the whole system can just fall completely out of sync.
So Lamport steps into this chaotic environment, and looking at his background in our sources, the most crucial detail, the key that really unlocks his entire approach to computer science, is that he wasn't actually a computer scientist.
No, he was fundamentally a mathematician.
Right. Born in 1941 in Brooklyn to a Jewish family of Belarusian and Polish descent. He goes to the Bronx High School of Science, gets his Bachelor of Science in Math from MIT in 1960, and then he heads over to Brandeis University.
And he's not just dabbling here.
No, not at all. He gets his PhD in 1972, focusing on singularities in analytic partial differential equations.
Which is heavy, heavy math. We really have to put that into the context of the 1970s tech world.
Right, because things were very different then.
Early computing was essentially the Wild West. Programmers were basically hackers in the traditional sense.
Just figuring it out as they go.
Yeah, they were building things, stringing code together, and using a lot of trial and error to see what stuck. If it worked most of the time, they shipped it.
Move fast and break things, decades before it was printed on a t-shirt.
Exactly that culture. But Lamport enters this wild frontier carrying the incredibly rigid, structured toolkit of advanced theoretical mathematics.
He wasn't about trial and error?
Not at all. He didn't want to build a system that just happened to work most of the time. He wanted to mathematically prove that a system must work correctly all of the time.
Which brings us to the first major hurdle he tackled, the problem of time.
Yes, time is a huge issue in these systems.
So in 1978, he publishes a paper called Time, Clocks, and the Ordering of Events in a Distributed System.
Legendary paper.
Our sources note this is among the most cited papers in the entire history of computer science.
It really is.
And to understand the problem he was solving, I was thinking about how we experience bad networks today. Imagine you're in a massive, unruly group text with 50 friends trying to coordinate dinner plans, but your cellular network is glitching out.
Oh, a very relatable modern nightmare.
Right, so messages are arriving completely out of order. Someone says, let's get pizza, another says, I hate pizza, and a third says, sounds great, I'll order it.
Total chaos.
But because of the glitch, you receive the sounds great message on your phone before you receive the let's get pizza message. Total confusion.
The causality is broken there. Because the messages arrived out of sequence, you can't tell what event caused the other event.
And in a computer network, servers are doing this thousands of times a second.
Millions even.
How do you know what happened first if there's no master clock keeping everyone on the exact same second? I mean, why can't they just look at their own internal clocks and stamp the time on the message?
Well, because physical clocks on different computers will always drift apart.
It's like watches getting out of sync.
Exactly. Even if they're off by just a few milliseconds. In the computing world, a millisecond is an eternity.
Wow.
Plus, network cables have different latencies based on physics and distance.
Yeah.
So Lamport introduces a completely brilliant concept called logical clocks, and something he termed the happened before relationship.
Okay, break down the mechanics of that. How does a logical clock actually keep things straight without a real clock?
He essentially decoupled the concept of time from physical reality.
Okay.
He said, we don't need to know the exact time of day an event happened. We just need a mathematical way to prove that event A happened before event B.
So it's more about the order of things.
Right, so instead of a timestamp, every computer just keeps a simple numerical counter.
Like a tally counter, 1, 2, 3.
Yes, exactly that. When a computer sends a message, it attaches its current counter number, say number 5.
Okay, makes sense.
When the receiving computer gets that message, it looks at the number. If the receiver's own counter is only at 3, it immediately updates its counter to 6.
It bumps it up.
Yeah, it updates it to 1 higher than the message it just got.
Oh, I see. So it forces the receiving computer to acknowledge that whatever it does next must have happened after that incoming message.
What's fascinating here is the sheer elegance of the solution. By shifting the focus from physical time to a logical sequence of numbers, Lamport gave the network a way to mathematically agree on the history of events.
Without even knowing what time it actually is.
Right. Even if the messages take different paths and arrive at different physical times, those embedded counters prove the causal chain.
He essentially invented a way for the universe of computers to agree on their own timeline without ever needing a watch.
Which is huge.
And this foundational theory is exactly why he won the Turing Award in 2013, which is widely considered the Nobel Prize of Computing.
And completely deserved.
The committee specifically praised him for imposing clear, well-defined coherence on seemingly chaotic systems.
It is the absolute bedrock of decentralized networks. We wouldn't have the internet as we know it without it.
But sorting out the timeline is only the first battle, right?
Right.
So Lamport gets these autonomous computers to agree on what happened and when. Now, they actually have to share resources and perform tasks without crashing into each other.
And this is where things get really complicated.
And this is where we get into Lamport's incredible knack for naming things. He came up with wonderfully quirky names for these highly complex algorithms. Let's talk about the bakery algorithm.
Yes, the bakery algorithm. This was his solution to a problem called mutual exclusion.
Mutual exclusion, meaning two things can't happen at once.
Precisely. Imagine two separate computer processes, or threads as we call them, both trying to edit your bank account balance at the exact same millisecond.
That sounds dangerous.
It is. One is depositing a check, the other is paying a bill. If they both grab the same piece of data at the same time, the system crashes, or worse, your balance gets corrupted.
Oh, man.
They need to mutually exclude each other. Only one can go at a time.
And Lamport solves this by comparing computer servers to a crowded deli. The imagery is fantastic.
It's a great analogy.
You walk into a busy bakery, you want to buy a cupcake, but 10 other people are crowded around the counter. If everyone shouts their order at once, the baker gets overwhelmed.
Total chaos.
So, what do? You walk over to the little red dispenser and pull a paper ticket. You get number 42, and you wait until the baker calls 42.
It maps perfectly to human behavior. Lamport's bakery algorithm literally programs the computer threads to take a digital ticket.
Okay.
When multiple threads want the same resource, the algorithm assigns them an escalating integer. The thread with the lowest number goes first, finishes its job, and then the next number is called.
It's so simple.
It guarantees fairness and prevents the system from locking up.
It takes a highly abstract data collision problem and grounds it in everyday logic.
Yeah, he was brilliant at that.
But a bakery assumes everyone is acting in good faith. What happens when the computers aren't just eager, but they are actually broken, or even maliciously trying to destroy the network?
That is a much darker problem, and it leads to one of his most famous concepts. The Byzantine Generals Problem, which he published in 1982, alongside Robert Shostak and Marshall Pease.
Walk us through the scenario. Why Byzantine generals?
Well, they frame the problem as a historical military dilemma. Imagine a group of generals from the Byzantine army, each commanding a portion of the troops, and they've completely surrounded an enemy city.
Okay, setting the scene.
They need to agree on a single plan of action. Either all of them attack together, or all of them retreat together.
High stakes. If they coordinate, they win. If only half of them attack, the army gets slaughtered.
Precisely. The generals are geographically separated, so they can only communicate by sending messengers back and forth between their camps.
Right, like passing messages in a network.
Exactly. But here is the catastrophic catch. Some of the generals might be traitors,
Oh, wow.
and these traitors will intentionally send false messages. They might tell General A we are attacking, while telling General B we are retreating, just to sow maximum confusion.
So, as a loyal general receiving these conflicting messages, how in the world do you figure out the truth?
It's a tough spot.
How do you reach a consensus when you know some of the data is completely fabricated?
You do it through multiple rounds of voting and verifying. In Lamport's mathematical model, General A doesn't just listen to General B.
Okay, what does he do?
General A also asks General C what General B told him. It creates a matrix of shared information.
Oh, so they cross-check everything.
Exactly. If a general receives a conflicting command, the algorithm looks at what the majority of the other nodes are reporting. The math proves that as long as more than 2/3 of the generals are loyal, they can root out the traitors and reach a unanimous, correct decision.
And in modern computing, the traitors are servers that have suffered a hardware failure or maybe they've been hacked.
Right? Or a bug in the code.
And they are sending corrupted data to the rest of the network. The industry calls this a Byzantine failure. So, what does this all mean for us today?
If we connect this to the bigger picture, without Lamport's solutions for Byzantine fault tolerance, modern networks would be terrifyingly fragile.
Like, they would just constantly break. Yes. For example, every time a commercial airplane is flying, its internal sensors are constantly checking with each other, using fault-tolerant algorithms to ensure a single broken sensor doesn't crash the plane.
That's horrifying, but I'm glad the math is there.
Or when a global financial database updates, it has to guarantee that a corrupted server in one country doesn't silently infect the ledgers in another.
He also tackled consensus with the Paxos algorithm, right? Which helps databases agree on updates.
Yeah, Paxos is huge in database management.
And he co-developed the Lamport algorithm, which is just mind-bending. It essentially allows a massive moving network to take a snapshot of its global state, freezing a consistent picture of the system without stopping the actual work.
And we can't forget the Lamport signature, which our sources highlight as an early prototype for the digital signature.
Right.
It really laid the groundwork for modern cryptography.
It's just an avalanche of foundational work. So you'd think the guy who is busy solving the underlying physics of computer networks, preventing Byzantine collapse, and prototyping digital security, you'd think he wouldn't have time to worry about, say, formatting text documents.
You would certainly think so.
Here's where it gets really interesting. In the early 1980s, Lamport decides he needs to write a book.
Just a personal project.
Yeah. And at this time, another towering figure in computer science, Donald Knuth, had created a typesetting system called TeX.
Right, TeX was incredibly powerful for laying out complex mathematical formulas, but it was notoriously difficult to use.
Very steep learning curve.
It required the writer to act almost like a traditional typesetter, manually coding the placement of text.
It was essentially asking a mathematician to become a graphic designer just to write a paragraph.
Exactly.
Lamport didn't want to deal with that. Because he just needed to format his own book, he started writing a set of macros, basically shortcut commands, on top of text.
Just to make his own life easier.
Right, to make it easier for him to focus on the writing rather than the layout.
He built a system where you could just use simple tags to define a chapter or a section, and the software would automatically handle the formatting rules behind the scenes.
And those personal shortcut macros became known as LaTeX.
Which is huge in academia.
He released version 2.06a in September 1984 and version 2.09 in August 1985.
I have to push back on this a bit. Are you telling me the architect of modern computing systems is also the unintentional hero of every college student, academic, and scientist trying to get the margins right on a math paper?
It really is true.
He invented a legendary software tool just because he wanted to format his own book.
It sounds accidental, but if you look at the through line of his career, there is a very clear pattern.
What's the pattern?
Whether he is looking at a chaotic server network with messages flying out of order, or a chaotic document where the math equations aren't lining up, Lamport's instinct is exactly the same.
He hates the mess. Yes, he cannot abide a system that lacks formal rules. He imposes elegant mathematical structure wherever he sees chaos.
And he didn't just write the code and hide it. Addison Wesley approached him in 1983 to turn his user manual into a published book.
Which was a massive success.
LaTeX, a document preparation system, comes out in 1986 and purportedly sells hundreds of thousands of copies. And then he just steps away.
He was done with it.
Yeah, in 1989, at a TeX user group meeting at Stanford, he hands over the maintenance and development of LaTeX to the LaTeX 3 team.
Because for Lamport, the problem was solved.
Hmm.
He had built the mathematical structure, it functioned beautifully, and it was time to let others maintain the plumbing while he moved on to the next major theoretical challenge.
Which brings us to the final and perhaps most challenging chapter of his career.
The quixotic quest.
Exactly, because Lamport's desire to impose structure culminated in what seems to be a lifetime mission, forcing software engineers to actually use math to verify their work.
This gets to the heart of a massive vulnerability in how software is built today.
We mentioned earlier that he introduced temporal logic to computer science. He created the temporal logic of actions, or TLA, and later a language called TLA plus S.
PLA plus S.
Our sources describe TLA plus as a language for specifying and reasoning about concurrent and reactive systems.
Whoa, hold on. Reasoning about concurrent and reactive systems.
It's a mouthful.
Let's translate that for a second. What does TLA plus actually do?
Think of it like an architectural blueprint for software.
Okay.
Before you pour a single ounce of concrete for a skyscraper, you run the math to prove the building won't collapse in a hurricane.
You hope so, yeah.
But software engineers rarely do that. They write the code, they run some tests, and if it doesn't crash during the tests, they ship it.
Right, but testing only checks the specific paths the engineer thought to test. It doesn't check the weird million-to-one edge cases.
Exactly. TLA Plus is a way to write out the logic of your system as a mathematical formula before you write the actual code.
So you're writing math, not code. Yes. Then a tool called a model checker explores every single possible state the system could ever be in.
Like simulating everything.
It doesn't just guess. It mathematically proves that your logic is flawless and that the system will never fail under specific conditions.
He literally wrote a book on it in 2002 called Specifying Systems. But I love how Lamport himself described it in our sources. He called his work on TLA plus a quixotic attempt to overcome engineers' antipathy towards mathematics.
It is a brilliantly self-aware quote.
He's calling himself the tech world's Don Quixote. But instead of riding a horse and fighting windmills, he's just out there trying to get stubborn software developers to eat their mathematical vegetables.
This raises an important question for anyone listening, because we all rely on these systems.
We do.
When companies are building critical digital infrastructure today, many still avoid that level of mathematical rigor because it's difficult and time-consuming.
It slows them down.
Right. Which means our current networks are far more vulnerable to bugs and crashes than they need to be. Lamport has spent the latter half of his career trying to give developers the tools to build completely bulletproof systems.
And looking at his legacy, the scientific community clearly recognizes the magnitude of what he's accomplished.
Oh, absolutely.
Instead of just listing off his resume, it's enough to say he has essentially won the highest possible honors across 3 different disciplines: mathematics, engineering, and computer science.
A rare feat.
The Turing Award, the Dijkstra Prize, the von Neumann Medal, memberships in the National Academies of both Sciences and Engineering.
He didn't just contribute to a field, he practically invented the rules of engagement for an entire era of computing.
But maybe the most culturally fascinating honor happened in 2020. The Solana blockchain platform, which is a massive decentralized crypto network, decided to name its smallest unit of currency after him.
Which makes total sense.
Yeah, 1/1000th of a sol, which is 0.00000000001 sol, is officially called Lamport.
It's an incredibly fitting tribute. Blockchain networks are entirely dependent on consensus algorithms, digital signatures, and Byzantine fault tolerance.
They couldn't exist without it.
No. The entire crypto industry is essentially running on the theoretical rails that Lamport laid down in the early 1980s.
It is wild to think about. So just to pull all these threads together from our deep dive.
Let's recap.
We started with a math student in the 1960s who looked at the messy, trial-and-error world of early computing and decided to bring an ironclad sense of proof to the frontier.
He wanted certainty.
He figured out how to tame the chaos of distributed networks using logical clocks, so autonomous machines could agree on the passage of time without a central watch.
That happened before relationship.
Right. He solved mutual exclusion with deli bakery tickets and thwarted malicious computers by solving the Byzantine Generals Problem with rigorous voting math.
He fixed the traitors.
He took a massive side quest to invent LaTeX, revolutionizing how the world formats academic papers. And he has spent decades trying to save engineers from their own sloppy code by championing tools like TLA plus size.
He fundamentally changed the invisible rules of the digital world.
He really did.
You don't see his algorithms when you're scrolling through your phone, but they are the bedrock keeping that entire experience from just collapsing.
So what does this all mean for us moving forward? We are moving incredibly fast toward a future that is even more decentralized than the internet of today.
Without a doubt.
We're looking at AI-driven autonomous systems, massive crypto networks, and billions of connected devices that have to constantly communicate and agree with each other without any human oversight.
It's only getting more complex.
Given that modern crypto platforms literally named their currency after him because his early prototypes were so vital, well, as we look toward this wildly complex automated future, will Lamport's foundational math from the 1970s and 80s be the only thing keeping our future digital society from descending into total Byzantine chaos?
It's a huge question.
It's something to think about the next time you hit send and expect that invisible machine to work perfectly.